Okay. So, next we are back again. So, let us take another example. Say 4000 or a 4500 upon 225 volt, it is a step down transformer, 50 hertz. 50 hertz means the frequency, right? F is equal to 50 hertz. Single phase transformer is to have an approximate EMF per turn of 15 volt, that is given, and operate with a maximum flux of 1.4 Weber per meter square. Calculate the number of primary and secondary turns, cross sectional area of the core, right? These two things we have to determine. So, EMF per turn is equal to E1 upon N1 is equal to E2 by N2 is equal to 15, it is given. Therefore, N1 is equal to E1 upon 15, that is also V1 upon A1, right, is equal to V2 upon N2 is equal to 15, that way you can make it. So, it is given 4500 by 15, so you will get it is 300, because it is primary side was 4500 volt. Similarly, secondary side 225 volt. So, N2 is equal to 225 by 15. So, it is 15, right, N2 is 15. Now, we know U1 is equal to 4.44 phi m F into N1. Therefore, phi m is equal to, you just put E1 value and all these values. So, E1 is 4500. So, you will get 0.0676 Weber. So, A, we know phi m is equal to A into flux density, right. So, A is equal to phi m by B max. So, phi m is given, maximum flux density 1.4 Weber per meter square is given. So, it is basically 0.0483 meter square, therefore, 483 centimeter square, right. So, this now next is the transformer on no load, right. When transformer on load, when transformer is on load. So, first this transformer on load. So, first when you will go through this, first you draw this circuit, right, then we will see. So, if you draw this your what you call this circuit. So, this is your primary side and this is your secondary side, a load is connected, Now, from our magnetic circuit, look, this R1 and X1, these are the two your resistance and reactance of the winding. These two resistance we put it here, right, as if nothing is here. So, this is your what you call E1. If you neglect all this, then V1 is equal to, is the magnitude wise, V1 is equal to E1. But when it is loaded, at that time this is R1 X1. So, this is the voltage. If it is an ideal transformer, R1 X1 is here. So, this is V1, this is E1 and this is V1, and arrow tips means it shows positive, right. And similarly, here a load is there, ZL is the load, right, and this is also voltage across the load is V2, and this R2 and X2 is the secondary side, that resistance and reactance. So, in that case, so earlier for no load cases we have seen that your what you call there was no current flowing in the secondary, right, and only your what you call that on the primary side an alternating voltage was applied, and this no load current that is your what you call the current I0 is very small, that is called your exciting current. It has two components, one is responsible for that your core losses, another is for magnetizing component that is responsible for producing flux. Now, in this case it is connected to the load. Now, before going to anything, so this is my N1 turn and this is N2 turn, primary and secondary windings, and this voltage is E1 and this voltage is E2, right. Your what you call E1 and E2 voltage, basically you can say this is an ideal transformer induced voltage. So, now if you apply your what you call that your magnetic circuit you have studied, the right hand rule, suppose this is the direction of the current is taken, let me clear it. So, this is the direction of the current is taken, right. So, if you grasp the conductor in the direction of the flow of the current, you will see thumb is up. So, flux direction from this side will be phi, right. Now, as load is connected, if load is connected, therefore, the current will be flowing like this. So, again if you wrap the your what you call conductor in the direction of the current, you will find this one also will be this way. That means, effective flux will be getting reduced. So, in that case what is happening, that EMF produced by this one, say by this one, it is sorry not EMF, MMF produced by this one will be N1 I1, and right, and this one will be N2 I2. Actually, it will be N1 I1 is equal to minus of N2 I2. It is something like this. Suppose, let me clear it. Suppose I have this transformer. I have that this is the transformer symbol. I have the transformer. Say this is my current I1, right. Let me clear it. Let me clear it. Let me make it a little better way. Just hold on, right. Just hold on. Suppose this is my transformer, right, and current actually flowing here is say I1 for example, and turns here it is N1, and this is my secondary side, right, primary secondary side, and here also say current, say this is I1, this turns ratio is say N2, and say current is here it is I2. So, I am taking just entering, put a dot here for an ideal transformer. So, you will see MMF on this side your I1 N1 and this side plus N2 I2 is equal to the reluctance into phi, right. The way we have done it, that you are what you call both current are entering into the dot, the magnetic circuit whatever you have studied, right. In other, if you do so, you will find these two are additive, because you apply your what you call right hand rule according to this. If you do so, but for an ideal transformer, the reluctance, you look at the assumptions whatever made in 4, the reluctance R is equal to your 0, right. If it is so, that means my N1 your what you call I1 N1 plus I2 N2 is equal to 0. That means, let me clear it, that means my I1 N1 is equal to minus your N2 I2. That means I1 and I2 there will be an antiphase. N1 N2 the constant, it is a turns, right, and I1 and I2 will be in antiphase. So, this is one way, and this is another than this one. That's why as it is minus. So, we have if we put a dot here, and if we put a dot here, right, if you take the direction of the current like this and this, so N1 I1 your is equal to your minus N2 I2, that means they are in antiphase, right. That means that is why the direction of the current is this way, that is going to the load. So, let me clear it, right. So, this is your what you call that when transformer is a load. Therefore, now this equivalent circuit actually we have seen that write up is there, later you can go through it, but whatever I have told from my mouth, just listen, write up is there about this. So, the R1 and X1 is the primary side resistance and reactance, and this is actually we are meant to, this is your what you call that IC and IM, that is your primary side we are giving the alternating supply. So, this IC current where your what you call a coal loss component is there. So, it can be represented by an equivalent resistance, right. Similarly, magnetizing current IM responsible for producing no load flux, right. So, it can be represented by your what you call by your what you call an inductance. So, and this is the current I0. So, and that means these two are parallel circuits. So, I give you that I0 is equal to IC minus GIM, and this is the secondary side, that R2 and X2, and this is the current flowing to the load. This is that your that ferromagnetic material primary winding secondary so on, and this is the load, and this is the voltage across the load is V2. Anybody arrow tip means instantaneous polarity plus, and this is minus, and this is N1 turns, this is N2 turns. Now, I am clearing it. Now, current from here, from the source, from the supply, it is I1, but part of the current that I0 is going here. I0 is equal to your this IC minus GIM. Rest the current is I2 dash. That means I in phasor sum that I1 is equal to your I0 plus I2 dash, right. So, in this case what will happen? This is the current going through the primary winding. Earlier I saw I1 because for ideal transformer all these things were neglected. Now, this current I2 dash N1 as per our this thing, this is I2 dash N1 MMF, this thing is equal to I2 N2. So, I2 dash when you solve the numerical, it will be N2 upon N1 I2, this way we will do. But in that our explanation whatever was there, that is actually should have come I2 N1 is equal to minus I2 N2, right. So, just in antiphase, that means I2 dash and I2 actually in antiphase. If this I0 is neglected, then I2 dash is equal to your I1. That is why I wrote N1 I1 is equal to N for an ideal transformer, right. So, that means MMF of this side primary side must be equal to mm of the secondary side as a magnitude, and this sign comes, right, and this sign also I told you. So that means when you will draw the phasor diagram, that means this I2 dash and this I2 will be in antiphase, that means 180 degree difference of the phase shift. So in this case, so we know that U1 is equal to minus N1 d phi by dt. So we know U1 is equal to this much, right? This we have seen in magnetic circuit also. We have solved one or two numerical. So this is my U1 and this is my U2. Earlier this thing is given. Now if you look at the phasor diagram, let me reduce the zoom, right? So if you see the phasor diagram, first one or two things let me tell you. This is nothing. The way it was there, I have made it. This is also nothing. Right? It is cut. So in this case, let me clear it. In this case, that V1 and U1 balance is lost, because it is on your what you call, it is on loaded, secondary side is loaded, and V1, if you look into the circuit, first let me explain here. So V1 is equal to, that is your minus E1, then this one is I1 R1, and this one 90 degree with that, this is 90 degree because it is reactance. So I1 R1, so this is my V1, right. So let me clear it. So if you just hold on. So if you look into the circuit, right, so when we draw this your phasor diagram, so V1 will be, when we are taking that V1, earlier for ideal transformer V1 is equal to minus E1, but now this RB of the loaded, because of the transformer is loaded, secondary side is loaded. So I1 R1 plus j I1 X1 tan has come. So that's why V1 is equal to minus E1 plus your I1 R1 plus j your I1 X1. That's why this phasor diagram your what to call, this phasor diagram is V1 is equal to your minus E1 I1 R1 plus your j I1 X1. This is this one. And second thing is that if you look into this, that your I1 is equal to I2 dash plus I0. When you will make it, you see the circuit diagram. Now this is my I0, that your no load current, and this is my I2 dash, and this is your I1, right. But I2 dash and I2, the secondary current, must be in antiphase. So that's why this one is I2. It is written here. This is I2. Actually, slightly it is this thing was. Suppose if it is there, if this is my I2 dash, then your what you call, then this one will be my I2. They will be in antiphase, right, because of that convention. So that's why this is my I2 dash and this is I2. I2 is drawn here. This phasor is I2. So let me clear it. Therefore, in the secondary side, so E2 will be equal to, if you look, E2 will be equal to V2 plus I2R2 plus JI2. If you apply, just let me clear it. If you apply KVL in this circuit, right. So this is your E2, right. In this circuit also, this is my E1, this is your E2, and this is plus minus, right. So if you apply your what you call, if you apply KVL, then your E2 will be equal to, right, this is your I2 R2 plus j I2 your X2 and plus your V2, right. So that is your E2 is equal to V2 plus I2 R2 plus j I2 X2. So you just apply KVL here, right. So that means this one, that is E2 is equal to V2 plus I2 R2 and this is I2 X2. This angle will be 90 degree, right. This angle will be 90 degree, and the resultant will be, this voltage drop will be I2 into Z2. Similarly here also this part will be I2 I1 into Z1, and this current I1 current I told you it will be I0 phasor sum plus I2 dash, right, and angle between V1 and I1 will be, say this angle is phi 1, right, and similarly angle between I2 and V2, this angle is equal to phi 2, it is shown here, it is phi 2, right. Only thing is that this portion is nothing, this portion is nothing cut, similarly this portion is nothing, right. So, I hope you have, and I2 and I2 dash are in antiphase. So, I hope that, and this is the same as before, that flux phi is a reference phasor, right. So, this is this phasor diagram, that transformer on low load. I hope you have understood this your what you call this just hold on, this phasor diagram. So, there should not be any confusion, right. When that, now the write up is there, just when whatever I said, when the transformer is loaded, a current I2 will flow in the secondary winding. The secondary MMF I2N2 sets up a secondary flux that tends to reduce the flux produced by the primary MMF. That means this is actually primary MMF, whatever it was, I2 dash into N1, and this is secondary MMF I2 into N2, and you use that what you call, you use that right hand rule, and then you will see the direction of the flux, and then you will see it will try to reduce that effective flux, right. That is what has been written here. You apply the right hand rule from the magnetic circuit, you grab the conductor in the direction of the flow of the current, and your thumb will be the direction of the flux, right. So, your I2N2 sets up a secondary flux that tends to reduce the flux produced by the primary MMF. As a result, U1 reduces, and the balance between V1 and U1 would no longer exist, right. Hence, on load, the presence of secondary MMF actually necessitates the production of primary MMF equal in magnitude, but opposite in direction. That is, your N1 I2 dash is equal to minus your what you call N2 I2. If your I0 is neglected, then I2 dash is equal to I1. Next is the little bit of construction of the transformer. So, this is I have taken from a book, right. So, generally that wherever we solve the numericals and other things, that is okay, but very equivalent circuit. But if you look into that low voltage, that is this is core type transformer, that low voltage winding, and above that your high voltage winding, how they are there, and this is laminated core. That is your real, that is your practical transformer. And if the cell type transformer is there, if you look into that, you will find low voltage winding, then high voltage winding, then low voltage winding, high voltage winding, right. So, these are the two different type of construction. Only one thing, small thing I will tell you, that you read any book and see the differences between the core type and your cell type. What is the main difference, right? This you should go of your own. Here I am skipping it, that thing, right. So, in this case, this kind of construction is made because it is core type and cell type. The low and high voltage windings are wound as shown in reduce the leakage flux, right. And similarly, for power transformer rated possibly at several MVA and operating at a frequency 50 Hz or 60 Hz, that is USA actually it is 60 Hz, and 50 or 60 Hz both are there in Japan, right. The core material used is usually your laminated silicon steel, the laminations reducing actually eddy current, that is why laminated, and the silicon steel keeping hysteresis loss to a minimum, right. And large power transformers are used in the power station, main distribution system, and in industrial supply circuits, right. So, small power transformer have many applications, example including welding and rectifier supplies, then domestic bell circuit, imported washing machines, etc. I mean, so many things are there for small power transformer. Now, then another thing, this will not cover, just for general knowledge. For audio frequency transformers rated from a few millivolt ampere to not more than your 20 volt ampere and operating at frequencies up to your about 15 kilohertz, the small core is also made of laminated silicon steel. Application audio amplifier system. This is just for purpose of general knowledge, we will not study that. Radio frequency transformers, it is operating in the megahertz frequency region, have either an air core, a ferrite core, or a dust core. So, ferrite is a ceramic material having magnetic properties similar to silicon steel, but having high resistivity. Dust cores consist of fine particles of carbonyl iron or your permalloy, that is your nickel and iron. Application radio and television receivers, right. Now, next is transformer windings, usually of enamel, insulated copper or aluminum. If you, when you go through this in your college first year lab, you can see that your windings of the transformer, open transformer, right, and cooling in brief, air in small transformers and oil in large transformers, right. Cooling is a huge chapter, right, in electrical engineering for transformers. So, just to give you some general ideas. Now, equivalent circuit of a transformer, because we have seen transformer, but we have to obtain the equivalent circuit of a transformer, because we have to solve problems, how to solve the problem for an equivalent transformer, for a transformer. For that, we need to know the equivalent circuit of a transformer, right. So, generally what happen, that whenever look at that whenever a transformer, your what you call is loaded. So, load means say inductive load. So, suppose it resistance, that is load resistance is RL and say reactance is XL. J is not put anywhere, but when you solve the problem we have to put J, the complex operator, and voltage across the load is V2, it is given here, right. And this is R1 X1, the primary side resistance, V1 is the supply voltage, and current through this is I0, that is your what you call, that is your no load current, and this current I1 is equal to I0 plus I2 dash, that is phasor sum, right. And this current, your this side we can call it is I1 dash is equal to I2 dash, we can call also this is I1 dash is equal to say I2 dash, right. So, and this is also R2 X2, that means this winding as if nothing is there, they are ideal transformer. So, this portion is called ideal transformer, right. So, that means in this case your E1 by E2 is equal to N1 by N2. This is an ideal transformer, as if everything is taken out from the transformer and represented by two windings. So, this is E1 E2. So, it is this portion, that is why by dash line this portion is shown by ideal transformer, right. And current flowing through this load is I2 and this current is I1 and this is I2 dash. So, now what we have to do is we have to make an equivalent circuit, either it will bring either you bring all these parameters to the primary side, this is one way, or you bring all these parameters to the secondary side, either of these. So, we will take the secondary parameter to the primary side. So, how we will do it? So, then this is an ideal transformer, the way we have represented everything, as if this E1 E2, this is an ideal transformer, that is written here, right. So, and so equivalent circuit of a transformer, that is we have to, this way we will not solve the problem, we have to bring everything to one side, that is say primary side. Now, the equivalent circuit can be simplified by transferring the secondary resistance and reactances to the primary side in such a way that the ratio of E2 to E1 is not affected to magnitude or phase. That means, this one as if it is an ideal transformer. So, E1 E2 the ratio will never be affected, not R2 X2 as well as this load also will transform to the primary side. Now, if we do so, say resistance R2 can be replaced by inserting an additional resistance R2 dash in the primary circuit, such that the power absorbed in R2 dash when carrying current is equal to that in R2 due to the secondary current, right. For example, say take this circuit. For example, I want to bring this one, this side, my power loss will be the current magnitude, that is I2 square is the magnitude into R2, this is the power loss, right. Now, if I want to put that equivalent resistance similar to that on the your what you call on the primary side, then suppose I have a resistance here and suppose this value is R2 dash, right. Therefore, this side loss actually it will be R2 dash then your I2 dash square, right. So, this loss and this I2 square R2 loss both has to be your equal, such that I will get the value of equivalent R2 dash, such that your what you call that your E1 by E2 ratio everything will remain same. Only thing is that we have to insert one resistance, we have to find an equivalent is R2 dash, right. Whereas then the loss of this one R2 dash into I2 dash square is equal to I2 square R2, this has to be same, based on that only we will transform, right. So, if it is so, then in this case I2 dash square into R2 dash is equal to I2 square R2, right. That means, R2 dash is equal to my I2 square upon I2 dash square into R2, that is I2 upon I2 dash your what you call square into R2. Now, from this, and now I2 upon I2 dash is equal to N1 upon N2, because from this diagram your this one, this turns for this one, this turns ratio is N1 and this turns ratio is N2, right, and current here is I2 dash. Therefore, you can make it I2 dash into N1, that is the MMF of the primary side, is equal to MMF of the secondary side, that is N2 into your N2 into your I2, right. So, this is I2 and here it is N2. So, N2 I2 is equal to I2 dash N1, right. That means I2 dash upon I2 is equal to N2 upon N1, right, or I2 upon I2 dash is equal to N1 upon N2, right. So, that is what has been written here. So, that means here you substitute that I2 upon I2 dash is equal to N1 upon N2. Therefore, N1 upon N2 square into R2. But we have seen earlier that K is equal to, the K turns ratio is equal to N1 upon N2. Therefore, R2 dash will be K square into R2, right. By similar way, that reactance also can be transferred to that. So, X2 dash also will be K square into X2, right. So, if it is so, therefore, R2 dash is equal to K square R2 and X2 dash is equal to K square X2. So, now this side, your what you call the secondary side, resistance and reactance, that equivalent one transferred to the primary side, right. But this is an this is an ideal transformer, but load RL XL is there, V2 is also there. So, if we, and in that case what will happen, as all these things transferred to here. So, your secondary side, my V2 now is equal to A2, right, my V2 is equal to E2, right. So, if V2 is equal to your E2, therefore, because all these things transfer here and V2 is the voltage across RL and XL. So, what one can do is the primary side your equivalent one, then what will be the equivalent voltage of your this V2 to the primary side? It will be nothing but your what you call that K into your V2 will come to the primary side. So, in that case, and this RL and XL in similar way you can bring it to the primary side. RL also you can make RL dash, XL will be XL dash, that also can be transformed to the primary side, right. If it is so, similar way, if it is so, then if you look into this, that E1 by E2 is equal to N1 by N2 and E2 is equal to V2. So, E1 by V2 is equal to your K, therefore, E1 is equal to K into V2. That means this side voltage transformation, it will be K into V2, because it is ideal transformer, this transition is N1, this is N2. So, E1 upon E2 is equal to N1 upon N2, that is your E1 upon E2 is equal to your N1 upon N2, right, but E2 is equal to V2, because this thing is transformed to this side, right. So, E2 is equal to V2, that means your E1 upon V2 is equal to K, right, N1 upon N2 is equal to K, therefore, E1 is equal to K into V2, right. And let me clear it, and when you transform this RL and XL to this side, it will be then your RL into your K square. Similarly, it will be XL into K square, the way you have transformed this, that is your RL dash and that will be your XL dash. So, let me clear it. So, in this case, your this RL dash is equal to K square your RL and XL dash is equal to K square into XL, I told you, and your E1 can be represented by KV2. This is your E1, it can be represented by KV2, voltage across the load. So, this is actually equivalent circuit of the transformer. Then what we did, we transform all the secondary parameters to the primary side, right, and this is my V1, this one my primary, or what you call the side parameters, this one also primary side parameters, and secondary side we have transformed by multiplying your what you call the square of the trans ratio or transformation ratio, that is K square R2, K square X2, and this is K square, all that means all the parameters resistance and reactance you have to multiply by K square, and this should be KV2. So, this from the numerical point of view, this you have to keep it in mind, but question is that this I0 current, actually this I0 current is very small compared to the full load current, right. generally your 3 to 5%, right. So, if you make this kind of series parallel circuit, it will be not easy, it will take time for your what you call for solving numericals or computation. So, in that case what we will do, this branch actually without losing much accuracy, this branch we will put somewhere here, right, we will put somewhere here, and this branch will remove from here, and this will be my I0. So, error will be very less, right, for easy computation. If we do so, then this circuit, that your I0 is 3 to 5% of the full load current, circuit looks like this. So, that means we brought that one, that means at the beginning this is my I1 and this is I0 is going. So, in that case I1 is equal to your I0 plus I2 dash, right. So, R1, and this is the total resistance R1 plus K square R2, the total resistance. Load we are not considering, a load keep it separate. Then X1 plus K square, that is primary and secondary equivalent resistance, right. So, RE is equal to RE1 rather is equal to R1 plus K square R2, XE1 is equal to X1 plus K square X2, right. So, this is an approximate equivalent circuit, and this side voltage will be V2 dash is equal to say K into V2, right, and this is the supply voltage. So, if it is so, then this is the approximate equivalent your circuit referred to primary, right. RE1 is this one, XE1 is this one, this value called referred to the primary side, because everything we have brought it to the primary side, right. And similarly RL1 dash is equal to K square RL, and XL1 dash is equal to K square A or XL, that is the load parameters referred to primary. If you bring that other thing, suppose I want to take it to the secondary side, the primary parameters, then many things will change, including your RC, XM, everything. So, in that case it should have been R2 plus R1 upon K square, it should have been X2 plus your X1 upon K square. Similarly, it should have been your RL upon K square, and it should have been XL upon K square if it is referred to the your secondary side. Similarly, voltage also would have been changed, right. It should have been your divided by K instead of multiplication of K, right. So, both way will solve the numericals. So, take a simple example. A single phase transformer has 2000 turns on the primary and 800 turns on the secondary side. Its no load current is 5 ampere at a power factor of 0.2 lagging, right, because at no load power factor is very poor. So, assuming the volt drop in the windings is negligible, so we are neglecting the drop. Determine the primary current and power factor when the secondary current is 100 ampere at a power factor of 0.85 lagging, right. So, this is the problem, right. So, now we know I2 dash N1 is equal to I2 N2. Now, all formulas are known to you. I2 is 100 ampere at 0.85 power factor lagging, right. Therefore, I2 dash is equal to N2 upon N and I2. All the data are given. So, I2 dash you compute 40 ampere and it is 0.85 lagging, that is I2 dash. Now, secondary side power factor is 0.85. So, phi 2 is equal to 31.8 degree, right. So, this is your what you call that secondary side power factor that is given, right. In the problem it is given that your when the secondary current is 100 ampere at a power factor of 0.85 lagging. Now, I0 is given 5 ampere and cos phi 0 is 0.2 is given. So, phi 0 is equal to 78.5 degree. Now, if you draw the phasor diagram, that phi as a reference, and this is your V1 and this is I1 is equal to your I0 plus your I2 dash, and this is I2, and I2 and I2 dash are in antiphase. I told you, that is why this is I2 and this is your I2 dash. Everything, look at the look at this your what you call cursor, I am making it, right. This is I2 dash, and this is my I1 is equal to I0 plus this thing, and this phi 0, the angle phi 0 it is given, that is 78.5 degree, right. So, that means your I1 cos phi 1, that is this is my I1 and this is my your what you call that your cos phi 1, that is this OA, that OA is equal to actually OB plus BA. OA I am not writing here, it is understandable, just make it your projection on this your on this your V your what you call on this y axis, vertical axis, right, V1, right. So, OB plus BA. Similarly, this side if you make I1 sin phi 1 is equally basically I1 sin phi 1 is equal to OD, that is nothing but OC plus CD, right. So, all the angles are marked and your currents are also computed, right. So, you can make it I1 cos phi 1 is equal to I2 dash cos 31.8 degree plus I0 cos phi 0, right. Whatever it comes, so I1 cos phi 1 coming actually 35, right. So, if you make it, this AB actually is nothing but this component, just do it little bit yourself, you will get it, very simple, right. But everything I have marked for you. And similarly, your I1 sin phi 1 is equal to I0 sin phi 0 plus I2 dash sin of 31.8 degree. You will get your I1 sin phi 1 is equal to 25.98. So, this I1 cos phi 1 and I1 sin phi 1 you square and add it, right. If you do so, you will get I1 is equal to 43.6 ampere, because sin square phi 1 plus cos square phi 1 is equal to 1. And if you divide this I1 cos phi and I1 sin phi 1, I1 sin phi 1 by I1 cos phi 1, you will get, you divide it and get it phi 1, you will get tan phi 1 is equal to something. So, phi 1 will be 36.6 degree. So, cos phi 1 will come your what you call 0.8, right. So, this is the answer. Another one is a 2200 220 primary side this volt, secondary side this volt, step down transformer, single phase 50 Hz, frequency f is 50 Hz, has resistance 1.25 ohm and reactance of 4 ohm in the high voltage winding, and 0.04 ohm resistance and 0.15 ohm reactance in the low voltage winding. That is, primary side is this much and secondary side is this much is given, right. So, calculate the equivalent resistance and reactance of low voltage side in terms of high voltage side, B equivalent resistance and the reactance of high voltage side in terms of low voltage side, both side we have to get it, right. So, R1 is given, R2 is given, X1 is given, X2 is given, R1 X1 for primary side, R2 X2 for secondary side. K is also given, N1 by N2 is equal to V1 by V2 is equal to this much, is equal to 10, right. So, R2 dash for the refer to the your what you call primary side, R2 dash will be K square R2, that means 4 ohm, right. All data you put, right, and X2 dash will be K square X2, so 10 square into 0.5, so 15 ohm. Therefore, in terms of high voltage side, that is your primary winding side, high voltage means here primary side, the way we have made it, right. Here your primary side is the high voltage side, say here it is high voltage side, this is this side we are making primary side, so high voltage side. So, in this case your what you call RE1 will be R1 plus R2 dash, you add, you will get 5.25 ohm. Similarly, X1 will be X1 plus X2 dash, you add, you will get 19 ohm, right. Now, B part is referred to the secondary side, in this case it will be divided, that is R1 dash will be that because R1 X1 you have to transform to the secondary side, not R2 X2. R2 X2 will remain in the secondary side, or in primary side you are transforming to the secondary side, that is high voltage side you are taking to the low voltage side. So, in that time your high voltage side resistance reactance, it has to be divided by your K square. So, that is why R1 upon K square. So, it is 1.25 over 10 square 0.0125 ohm, and X1 will be X1 dash will be X1 upon K square, it is coming 0.04 ohm. So, in terms of low voltage side now, that is your secondary side, right, it is RE2 is equal to R2 plus R1 dash, you add it, it is 0.0525 ohm, right, and X2 dash if you add it, it will be your 0.19 ohm, right. But one thing, look here, it is 5.25 ohm, it is 19 ohm, and secondary side it is 0.05 to 25 ohm, and if you want to bring whole thing to the your what you call your to the your primary, your what you call primary side, if you multiply this by 100 10 square, it will be 5.25 ohm, and this one if you multiply by 10 square, that is 100, you will get 19 ohm, or vice versa, right. From that you can check whether calculation is correct or not, right. So, this is one, and your thank you very much, we will be back again.